Hello.
What are you doing? Okay. We will start by describing the assignment of the course assignment, the project. The course, okay?
Okay.
Okay. This is the group. It is a group project for this course, okay? I will read for you. It's a local area network simulation using Cisco Packet Tracer. The project details. Using Cisco Packet Tracer simulation software, simulate local area network which must consist of hardware details as follows. The hardware in your local network will be one dynamic IP personal computer, one static IP personal computer, one dynamic IP laptop, one DHCP server, and in the other column, the name in the Cisco packet tracer, how you will find the name. Oh, and one web server, one switch, connectors using wires. Use class C network with IP address of 192.168.1 and 3x. The report submission. Each group are required to submit three things, three files. One, group project report and must contain the title of the project, group members, full name, matric number and lecture group, introduction of the project, benefits of the project, relevant project screenshots with explanation, configuration details for each hardware, conclusion and references. Number 2, this is the first file. The file number 2 is the Cisco Packet Tracer project file you have to submit. And the 3, presentation file, the PowerPoint, not more than 10 slides. All this should be submitted by the group leader. So each group, you have to arrange yourself, will divide yourself into groups. Each group contains 4 students. One of them is the leader, and the leader have to submit the 3 files described in the file, in the project file. So Dr. Osama already submitted to you on the system the project and the link of the Cisco Packet Tracer software. He submitted for you this version, free version, because it's normally it's not free. So you can download the tool and work on it. How to work on it? You can watch a video on YouTube, you can search and study and learn how to work on this project, or work on the Cisco Packet Tracer. You will find many videos. Okay, when is the submission? You start by today and for 2 weeks. So the submission date is March 14. March 14, okay? So everyone heard what are you going to do for the project course? The course project? Sorry, only the lead. So if anyone not heard about the project, you can tell each other about it, okay? Done? Any question about the project? Any question about the project? No questions. Okay. So we can start our lecture. Go back to our chapter 3 about signals and data in the communication system. Last time we learned about the signals and data. We learned some features for the signals like amplitude, which is the height of the signal. We learn about frequency, time, which is the period, this law, frequency and time. We learned about these units of conversion. Then we reached about to learn about the phase. The phase of the signal is another feature or attribute of the signal. It describes the position of the wave form relative to time zero. So the phase describes the position of the wave form relative to time zero, and we will have this example. In this figure, three sine waves with the same amplitude and frequency, but different phases. Different phases. So we said the phase is the position of the waveform. The position of the first waveform. Look how it starts. It starts by the beginning of the wave. We can represent the wave in another form, so it is represented by one cycle. Each one of these waves can be represented by one cycle starting by 0. This is 0 degree. This is 90 degree. This is 180. And this is 270 degree. This is at time 0. This is at 1/4 the time. This is at half the time. This is for 3/4 the time. And this is the full time. This is 0 and also 3, 6, 0. This is a full circle, complete circle. So in the figure A, 0 degrees, the phase starts by these 0 degrees, and so look at the direction of the wave. Imagine that we make a shift for, normally the waves can be shifted to the left side. This is the time axis. Suppose we shifted the wave to the left direction on the time axis, it will be like this shape. So 1/4 the time this wave starts before, see at time 0 where the wave starts. It starts at angle 90, right? This is angle 90 here. This is 90. Hmm. Okay. This is 90. This is 180, and this is 270, and this is 360. This is the one cycle I told you about here. Okay, so if we shift the wave to the left 1/4 the time period, it will be, the phase will be like this. It is the same sign, the same signal, but shifted 1/4 the time. In figure C, the wave was shifted half the time, 1/2 or 2/4, 2/4 the time. So it starts by 180. This is what we mean by the phase. So one feature of the signal or the wave, the sine wave, is the phase. We will learn more about this. There is an example. A sine wave is offset 1/6 cycle, 1/6 of the cycle with respect to time 0. So if it starts on 1/6 of the cycle with respect to time 0, what is its phase in degrees? We want to know what is its phase on degrees and radians. What we mean by radians? So let's stop here and learn what we mean by radians. It is another representation. I will share you another slide which explains what we mean by radians. The term phase describes the position of the waveform relative to time 0. If we think of the wave as something that can be shifted backward and forward along the time axis, phase describes the amount of the shift. So the phase describes the amount of the shift. It indicates the status of the first cycle. So at time 0, we can tell we started the first cycle. Phase is measured in degrees or radians. Degrees, like I show you, 360 degrees, or in radians, which is equal to 2 pi rads. So the degree one can be 2 pi over 360 rads. Another representation for degree 1. And 1 rad is 360 over 2 pi. Phase shift of 360-degree corresponds to a shift of a complete period. If the shift was 360-degree, so it is a complete period. A phase shift of 180-degree corresponds to a shift of 1/2 of a period, as we see in the previous example. And a phase shift of 90-degree corresponds to a shift of 1/4 of a period. You can take a screenshot of this slide. Stop. So now this is clear, right? So this is a shift correspond to 1/4 time with 90 degrees. This shift in C corresponds to 180 degrees, half round shift. Then if it is 1/6 of the cycle, how we can find the degrees and radians? Because we know that one complete cycle is 160 degree. Therefore, 1/6 cycle is 1/6 multiplied by 360. Then the degree is 60 degree. The phase is 60 degree. 60 degree multiplied by 2 by over 1/360 rads. So the representation will be, it's equivalent, 60 degrees, it's equivalent to 1.046 rads. That's how we find the phase in degrees. In degrees, it is 60, and in radians, it is 1.046. Another concept or feature of the wave is the wavelength. The wavelength in the transmission medium at time t. This is the wavelength. We can say this is a wavelength. So from the peak to another peak, it is a wavelength. And this is the direction of the propagation of the wave. So it's one cycle in the time period. Let's learn more about the signal domain. We have the time domain and frequency domain plots of a sine wave. So the sine wave can be represented in the time domain and can be represented also in the frequency domain. From the beginning, we learned to how it can be represented or plots in the time domain. So we learned that if this is the frequency is 6 hertz, so this is 1 second until here. 1 second, 1, 2, 3, 4, 5, 6. Yes, 6 hertz mean this is 1 second. A sine wave in the time domain peak value. The peak value is 5. The peak value or the amplitude is 5. Frequency is 6 hertz. And this is the time axis. How can be represented in the frequency domain? It is so simple. So simple. In the frequency domain, it started from 1 until 14. In the frequency domain at 6, because the frequency up was 6 hertz. So in the frequency number 6, we plot this wave. And what is the height or the peak value? It is 5. So one axis represents the amplitude and the other axis represent the frequency. The wave is at frequency 6 because the frequency here was 6, and the height at the amplitude axis is 5 because the peak value up was 5. Is it clear? Here, how we represent the wave in the time domain, and in B, figure B, we represent the wave in the frequency domain. A complete sine wave in the time domain can be represented by one single spike in the frequency domain, as we see here. So a complete sine wave in the time domain can be represented in one single spike in the frequency domain, one only. It's more clear. Where we can go to use this, the frequency domain is more compact and useful when we are dealing with more than one single sine wave. For example, we will see figure 3.8 shows three sine waves, each with different amplitude and frequency. All can be represented by three spikes in the frequency domain and will be more clear. See figure 3.8, the time domain and the frequency domain of three sine waves. In figure A, you can see the first wave at amplitude 15 with zero frequency, and pink, the second wave with the pink color. If we count, there will be 8 cycles, so its frequency is 8. The pink wave, its frequency is 8, and the third wave, which is in the green, if we count the cycle, they are 16. So the frequency is 16. So we have 3 waves in the time domain. How can be represented in the frequency domain? Using the frequency axis and the amplitude, the frequency axis and the amplitude axis. So wave 1 with frequency 0 and height 15. The second wave with frequency 8, so 8 on the frequency axis, and what is the amplitude? It is 10. And the third wave with 16F, and the amplitude is 5. So this is the representation in the frequency domain for the same 3 signals. Signals and communication. A single frequency sine wave is not useful in data communications. Usually, the data communications contain more than one single wave. So we need to send composite signal, a signal made of many simple sine waves. The single have many simple sine waves. According to Fourier analysis, which is a mathematics scientist, any composite signal is a combination of simple sine waves with different frequencies, different amplitudes, and different phases. So every composite signal is a combination of simple sine waves with different frequencies, different amplitudes, or different phases. Composite signals and periodicity. The composite signal is periodic, so the decomposition gives a series of signals with discrete frequencies, or the composite signal is non-periodic, so the decomposition gives a combination of sine waves with continuous frequencies, so the periodic. decomposition for composite signal gives a series of discrete frequencies, and the non-periodic composite signal, the decomposition gives a combination of sine waves with continuous frequencies. For more insight to the periodic and non-periodic, I brought to you the next file, and I can submit to the group. I'll stop now and share with you. To be more clear for you, the signals, periodic and non-periodic. Continuous time periodic signal. This is continuous time periodic signal. For the periodic, we mean the signal is said to be periodic signal if it has a definite pattern and repeats itself at regular interval of time. It repeats itself at the definite at interval, regular interval of time, regular interval of time. So every 1 second, for example, it repeats itself, the same wave. So this is a periodic. This is a periodic and continuous. This is also periodic and continuous. So what we mean by discrete time periodic? Discrete time periodic. This is a discrete time periodic signal. This one is it is not continuous, but it is regular. So this is periodic and discrete. This is also, it repeats itself at the interval of time. It repeats of itself. So if we focus, we can see a pattern at a specific interval of time. It repeats itself. For the continuous time, aperiodic. Aperiodic means non-periodic. So you can see non-periodic or aperiodic, it's the same meaning. Aperiodic. This one, this signal is continuous but non-periodic. So it does not repeat itself at a specific interval of time. Also, in the other side, this one, it is continuous but non-periodic. Why non-periodic? We cannot see a pattern. It does not repeat itself. And the fourth and the last, discrete and aperiodic, or discrete and non-periodic time signal. This one is discrete and non-periodic. So it does not repeat itself over the time, and it's at the same time discrete. So just to see example of these types of waves, let's go back to our so if the composite signal is periodic, we know now what's the meaning of periodic. The decomposition gives a series of signals with discrete frequencies. If the composite signal is non-periodic, the decomposition gives a combination of sine waves with continuous frequencies. So this example, 3.9, shows a periodic composite signal with frequency f. This type of signal is not typical of those found in a data communication. This is only an example of a periodic composite signal, but it is not typical in the data communication. We can consider it to be three alarm systems, each with a different frequency. The analysis of this signal can give us a good understanding of how to decompose signal. It is just an example of how to decompose signals. So if we focus, this is a composition of like three signals with different frequencies. One of them is continuous, and if you see the pattern is, this is the pattern of discrete. It can be an example of alarm systems with three frequencies. This frequency is different than this. This is another one, and this is the discrete one. In the data communication, we can have this, the decomposition of a composite periodic. This is a composite. We mean it is contain more than one sine wave. Decomposition of a composite periodic signal in the time and the frequency domains. In the time domain, the first one, A, time domain decomposition for a composite signal. So we can see the pink wave with the frequency F, the blue one with the frequency 3, and we understand when we say 3F means in the one cycle there are three, in one time unit there are 3 cycles of the wave. And the frequency 9. Frequency 9 is the black one, the black signal, the black wave in the signal. So we have 3 frequencies. How to represent in frequency domain? This is the pink one, the frequency F, and this the blue one in the frequency 3F and 9F. So this is 1, this is 3, and this is 9, with the amplitude, with the same amplitude. This is the representation with the same amplitude of the original signal. There are no numbers, but it is done by estimation. Okay. Figure 3.11 shows a non-periodic composite signal. The previous one was periodic, and we learn what's the meaning of periodic. And in 3.11, it is non-periodic signal composite, non-periodic and composite signal. It can be the signal created as an example. The non-periodic composite signal can be created by a microphone or a telephone set when a word or two is pronounced. So when you talk in your phone, each word have a different frequency, have a different signal. In this case, the composite signal cannot be periodic, because that implies that we are repeating. If it is periodic, then we are repeating the same time. Imagine that. If we say at the same time, all the conversation, so yes, 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 like this, it will be periodic. But normally, it's not like this. So we can talk more than one word, so it is non-periodic. So the time and the frequency domain of the non-periodic signal can be look like this. The time in the time domain, this is a non-periodic signal. It's like your talk in a phone. How it can be represented in the frequency domain? This is the frequency axis. This is the frequency axis. So each one of these, the number of waves in the single unit of time represent the frequency. So the frequency or the amplitude of the sine wave of frequency F, one of these frequencies. And as you see, the frequency is different. The frequency is different here in the non-periodic signal. So this is the same representation of the signal in the time on the right, on the left-hand side, the time domain, and on the right-hand side, the frequency domain. Now we are coming to learn about a new concept in the signal world, which is the bandwidth. The bandwidth and signal frequency, and the relationship between the bandwidth and the signal frequency. The bandwidth of the composite signal is the difference between the highest and the lowest frequencies contained in that signal. So it is the difference. So the bandwidth, we can write like this. Bandwidth equal the highest frequency F high minus the lowest frequency F low. This is what we mean by the bandwidth. So the bandwidth of periodic and non-periodic composite signals. In figure A, the bandwidth of the periodic signal. We can see different frequencies. The lowest one is 1000 and the highest one is 5000. So the bandwidth is equal the highest, which is 5000, minus the lowest, which is 1000. And in the non-periodic signal, and we can see this one is continuous, the same. We have the highest frequency and the highest, which is 5000, and the lowest frequency, which is 1000. So B equal the same quantity, 5000 minus 1000. If a periodic signal is decomposed into 5 sine waves, look at this example. If a periodic signal is decomposed into 5 sine waves with frequencies of 100, 300, 500, 700, and 900 hertz, what is its bandwidth? And draw the spectrum, assuming all components have the maximum amplitude of 10 volts. The solution, we said that the bandwidth B equal frequency high minus frequency low. So, what is the highest? It is 900 minus What is the lowest? It is 100. What is the answer? The frequency unit, what it is? 800 what? Hertz. We measure the frequency with hertz units. Okay, then the spectrum has only 5 spikes at 10, 300, 5, 7, and with the maximum amplitude of 10. So this is the bandwidth spikes. We said the amplitude is 10 for all 5 waves. Example 3.7. A periodic signal has a bandwidth of 20 Hz. The highest frequency is 60 Hz. What is the lowest frequency? Draw the spectrum of the signal. Contains all frequencies of the same amplitude. As we said, the bandwidth, you can try to solve this example alone. The bandwidth, which is 20 equals 60 minus f1. So we can inverse. And this is how we plot the spikes of this signal, the waves. This is another example that you can learn by yourself. So simple. If you have any question, you can come back and ask. We stop here at Fourier analysis. You solve the examples, study the examples, okay? If you didn't understand anything, you can ask next lecture, and we stop here at Fourier analysis. Okay, any question until here?
No.
Oh,
Everything is clear?
yes.
Yes. Yes.
Okay, thank you all. Thank you all for attending the class. Goodbye. Assalamu alaikum.
Thank you.
Thank you.
Welcome. Welcome.
Thank you.
Welcome. Assalamu
Thank
alaikum.
you.
Thank you.
You are
Thank
welcome.
Thank you.
You are welcome.
Thank you.